So per your guys' request, this video will be 30 minutes. So I have a timer set going to make sure I stop at 30 minutes. So this video will be properties and naming. And so we'll go through each property and name based off of the functional group. But first, I wanted to start with an introduction to intermolecular forces. I don't believe there's like this is formally in any of the chapters, but I believe that this will help you guys substantially in understanding the properties. So we have talked about bonds, specifically between molecules to make a compound. And these are intramolecular forces. So we had ionic bonds and covalent bonds, and I won't dig too deep into that because what we really care about is intermolecular forces. And these are bonds, or rather forces, between molecules, right? So, I'm sorry, between compounds. So we have three different types. London forces. Sometimes these are called dispersion forces. Dipole-dipole, and hydrogen bonds. So London forces or dispersion forces only occur between nonpolar molecules. I keep saying molecules when I mean to say compounds. Dipole-dipole occurs in polar molecules, and hydrogen bonds occur in polar molecules, but specifically with an F attached to an N, an F attached to a hydrogen, a nitrogen attached to a hydrogen, or a oxygen attached to a hydrogen. So we increase strength as we go to the right. So London forces being the weakest, dipole-dipole being intermediate, and hydrogen's bonds being the strongest. And this strength directly correlates to solubility, boiling point, and the melting point. So that will all come back into play here in a second. So first, starting with the property of alkanes, right? Alkanes are single bonded molecules. So here's an example of an alkane. So alkanes with no heteroatoms, so this is just carbon and hydrogens, because remember, heteroatoms are anything that aren't carbon or hydrogen. So alkanes are insoluble in water typically very hydrophobic. They dislike water. And in general, they have a lower melting point, boiling point than any other compounds of similar weight. So alkanes, using the same example, are only made up of carbon and hydrogens, and therefore only they're nonpolar and only exhibit London forces. Which makes sense, right? On our scale on the last slide, London forces had low melting points, low boiling points, and were lowest on the solubility scale. So what if I were to compare two molecules that were both alkanes, and I was asked to compare their boiling points? Which one has a higher boiling point? I'll put BP for boiling point. So an increasing amount of carbons increases the boiling point when we compare alkanes. So this molecule would have a higher boiling point as opposed to this molecule. This molecule has 3 carbons, and this molecule has 6 carbons. 1, 2, 3, 4, 5. I'm sorry, 5. So the next slide here, I have a little diagram, and you'll see this diagram throughout, because it's a picture I've cropped and then I start building up upon it. Don't necessarily memorize these numbers here. It's just to demonstrate how, as we increase the amount of carbons, we also increase BP. So looking at an OWL question 9, it's asking us to arrange the following compound in increasing boiling points. So to do this, I am going to first count the carbons. And so this molecule has 6 carbons, this molecule has 7 carbons, and this molecule has 5 carbons. So higher number of carbons equals higher BP. So therefore, the one with 7 carbons is going to have the highest boiling point, then 6, and then 5 would have the lowest boiling point. Next, we're going to talk about properties of alkanes and alkenes. So just a reminder, alkenes are anything with a double bond, and alkynes are triple bonds. So the properties are similar to alkanes. They're nonpolar, they're only carbon and hydrogens, so they only exhibit London forces. So this makes them insoluble. The same is true when comparing alkenes, an alkene with another alkene, or alkyne with another alkyne, in terms of trying to determine boiling point, is that the increasing carbons increases the melting or boiling point. But alkenes on general and alkynes have a lower boiling point and melting point than the same number of carbons in an alkyne. So it's a lot of words. basically, if I have a 4-carbon structure here, all single bonds, this is an alkane, and I have a 4-carbon structure here, but it's an alkene, it has a double bond, which has the higher BP? And so this rule that I'm trying to display here is that alkanes have the higher BP, the double bond ends up lowering their boiling point slightly, ever so slightly. So moving on to alcohols. So just a reminder, alcohols, anything with an OH group attached to it. These are genuinely really soluble in water, right? This is because this OH group, if we remember from our intermolecular forces slide, exhibits hydrogen bonds, which is the strongest intermolecular force. So these have, in general, high BPs, high MPs, melting points, and high solubility. So the general rule is that they are soluble with one hydroxyl group, one OH, per every 3 to 4 carbons. So as soon as you start going crazy and putting this crazy long chain, we have one hydroxyl group per, say, I don't know, 8, 9 carbons. Then we start to reach pretty insoluble territory because we have this long hydrophobic region. But in general, 3 to 4 carbons, 1, 2, 3, 4, oops, soluble. So like I said, this is because they're able to hydrogen bond. Because they have good solubility, and they have those hydrogen bonds, they have higher boiling points than alkenes, alkynes, and alkanes. So, oops. For example, if I were to ask which has a higher boiling point, and I was comparing 2 4-carbon structures, but one has a hydroxyl group, the group with the hydroxyl has the higher boiling point. And so here's that image I talked about again, but now I've, layered on another layer here. So again, don't memorize the numbers, but it's just to show you how even the alcohol with the 3 carbons is still higher boiling point than that of a, what is this? A 1, 2, 3, 4, 5, 6 carbon structure, right? So even the smallest number of carbons in an alcohol is still a much higher BP than an alkane. And this diagram doesn't show alkenes and alkynes, but if we wanted to throw them on here, we know that generally they have a lower boiling point than that of the same amount of carbons in an alkane. So the boiling point would be less than -42 C and less than 0 degrees C and less than 36 degrees C, less than 69 degrees C. I don't know for sure, but just because I haven't measured these, but we know that they would be, I can't put a number like how much less, but we know that they would be less. So now looking at property of ethers. So just a reminder, ethers is when we have an oxygen sandwiched between 2 carbon atoms, and then maybe we have some other stuff on the side. These are more soluble than alkanes, alkenes, and alkynes, but not as soluble as an alcohol. And this is because they exhibit dipole-dipole forces, right, which was the intermediate. So this puts them at, higher boiling points than alkenes, alkynes, higher solubility than alkenes and alkynes, but not as high as an alcohol. So if we were to rank these molecules, they all have 4 carbons. Let's say rank the boiling points. We'll say highest to lowest. An alcohol would be the highest, and ether would be the next highest, and an alkane would have the lowest boiling point. And so again, building on this image, I've now cropped in the ethers, in which we see that, right, they're somewhere between the alkanes and the alcohols, right? And so it's put definitive numbers on them, but yeah. So practice OWL question 10. Which of the following would you expect to be the least soluble in water? So here I have an example of a ketone, which we'll learn next week. But we see it has a oxygen group here, which means it displays, it's polar and displays dipole-dipole forces. Whereas this butane is an alkane, and as we know, is insoluble in water. So the alkane would be the least soluble. So next, this practice problem asks us to rank the boiling point of alcohol and ethers. And so this is like your question OWL 17. So this is an ether. We have an oxygen sandwiched between 2 carbons. This looks like just an alkane. I only see carbon and hydrogens. Where this is an alcohol because we end in a hydroxyl group. So alcohol is going to have the highest boiling point because of that OH group exhibits hydrogen bonds. The alkane is going to have the lowest boiling point because it's nonpolar and only exhibits London forces. And the ether is going to be intermediate in this case because the O makes it a polar molecule and exhibits dipole-dipole forces. So we've seen this slide, but I just want to reiterate. Maybe we haven't seen this slide. I honestly can't remember. I think, okay. So we're going to start going into naming. And so I just want to demonstrate something that's really important, is that we always want to consider the parent chain is the longest carbon chain in the molecule or in the compound. So hexane here right? If it's every point is a carbon, so 1, 2, 3, 4, 5, 6. Right? There's no branching chains here, so there's no, it doesn't get complicated. But when I start counting carbons here, I have 1, 2. Now I could go here, 3, but then my chain has stopped. And so there is a third carbon here, but as for the parent chain, I'm going to go 4, 5, 6. I want my parent chain to be as long as possible. And so again, this slide is just referring to parent chains. So again, looking at this next molecule, I could count 1, 2, 3. Now I have some options. I could come here, but I stop at 4, whereas opposed to if I come here, 4, 5. So I'm going to stick with, oh crap. I'm going to stick with my 4, 5. Because that's the longest parent chain. Looking at this molecule down here, we have lots of options. 1, 2, could go up and go 3 here. Or I could go 3. I could go 4 here or 4 here. Doesn't really matter because they both end with the longest chain at 4. So that's my parent chain. And the next molecule, 1, 2, I could go 3 here, I could go 3 here, I could go 3 here. I'm going to end up going 3 here because I have another carbon I can count, carbon 4. And so that's my longest parent chain. So the point I'm trying to get across in this slide is counting the parent chain. You want to make it the longest it can be. And so counting parent chain carbons is important in naming, which we're about to jump into. All right, so naming organic molecules is quite the endeavor. There's a whole rule book of naming. There's this whole system. It's called IUPAC naming system. It's this whole governing body that has gone out and decided to make all these complicated rules for naming organic molecules. But we will come back to this general naming rule in which we have a prefix, a parent, and a suffix. And so the prefix is naming any branches that are coming off your molecule. The parent is that parent chain of carbons that we were just counting in the last slide. And so this is going to be a number. And the suffix is going to be the primary functional group. So the parent name, right, I said is based off of the longest number of carbons in the parent chain. So if you have 1 carbon, you're using the parent name meth, 2 eth, 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, and 10 dec. So 5 on are prefixes we recognize from chapter 4, naming molecular compounds. But meth, eth, prop, and but might look a little might be a little unfamiliar. And so there's a mnemonic that I learned. So there was a mnemonic that I learned when I was in organic chemistry, and it was monkeys eat peanut butter. And it was a way of remembering that methyl was equivalent to 1, ethyl, the eat, was equivalent to 2, P, and peanut butter was prop, and B, and butter was 4. So let's name this molecule here. Let's start by counting the carbons in the parent chain. So I have 1, 2, 3, 4, 5, 6. So I have 6 carbons. This corresponds to the prefix or the parent name hex. We'll come back to that in a second. So first, to name this molecule, I would want to start with the prefix, which is any branches that are coming off. This molecule is easy. There's no branches. So next, I want to, So next I want to use the parent name based on the number of carbons. So for us, it's hex. And then I want to end in my functional group. So alkanes have the suffix ane. So this molecule is hexane.